Thank you very much, Vicky, and thank you for inviting us to this Friday Frontier series. We are very happy to be here and thankful for the opportunity. And we hope that it will be an interesting presentation. Now, Vicky already told you who we are. So if I do it again, I am Stefan Lindgren, a research engineer.
And I'm Carolina Larsson.
And we work at Lund University Humanities Lab. And I thought we'd say a couple of words about our workplace before we get into the project that we are presenting today. So Lund University Humanities Lab, it is a research infrastructure. We facilitate studying human behavior, communication, cognition, and culture. And we provide technology, equipment, expertise of different kind to different researchers. So we sort of started within the humanistic faculty, but it has turned out that the methods, the instruments, and the expertise that we have is useful for a lot of other people. So since last year, 2025, we are assigned as a core facility at Lund University. So any researcher or any student at Lund University is free to use the lab. And I point out the word free. It doesn't cost anything. And what we do, and it's not only Lund University, I should say, we have collaborations all over Sweden and all over the world, and people come here and do their research here. So what we do as a research infrastructure is that we provide methods and instruments and knowledge that can help researchers enhance their research workflow, help them try new methods that they maybe haven't thought about. And they come here and we provide training so they learn how to use the instruments. We provide expertise to help them set everything up. And we provide the instruments, and then we let them roam freely almost. And they can do their recordings here. And one reason that we let it be free is that there is a phase where researchers are looking into and maybe finding methods that they want to try, but they don't have the money for it. So we have quite a lot of sort of test projects or just to find out, does this work for what we are doing? So and as a research infrastructure, that is sort of what we do. But we don't own the research. The researchers own their own research. We just help them with methods and ways that they can continue with their research. I should also say that we have researchers working in the lab and sort of working with their own questions. But the thing that they do for the lab is usually connected to method development. So we can develop methods that other users then can use later on. So what do we provide? Well, we have eye tracking, world-leading eye tracking, so to measure what you look at. We have keyboard logging to measure how you write. We have EEG to measure what happens in the brain when you have certain stimulus. We have biopack that measures things like breathing and heart rate. We have motion capture, which will be the main talk here. We have a big 3D documentation suite that records anything from really small objects up to complete landscapes. We have an articulograph, which is a machine that measures how your tongue moves in your mouth when you're talking. And we have recording studios, an anechoic chamber. We have servers and archive servers. And of course, we have a unit that works with artificial intelligence and machine learning in different aspects. But what we want to look into today is motion capture. And motion capture was originally bought to study, for language research, to study body language and gestures. So it's an interesting thing because we all use it daily, but we don't think much about it. And it's clear that your body language is connected to your native language. So I'm a native Swedish speaker, so I will have Swedish body language. That's not a problem until I learn a second language. So I speak English with my mouth and maybe Swedish with my body, and then that could be misunderstandings maybe. That's a simple way. We look more into deeper things with this as well. We can look into things like the temporal aspect of a gesture. So how does the timing of the gesture affect the understanding of the gesture? Or we can look into things like what comes first. Is it the gesture or what you say with your mouth? So it's more, that's what it was originally thought to be used for. But motion capture can really record anything that moves. And the way it works is you have special cameras. They are infrared cameras that record. What you see here is small markers to the left. So the cameras can record the exact position in the volume in the room with sub-millimeter precision. And so you know exactly where the marker is. And then you can place a lot of markers on whatever it is you want to record. So the way it works is you select the volume you want to record, and then you place the cameras all around this volume, and you do a calibration so that the system knows where each camera is in reference to all the other cameras. So I have a short screenshot here where you see I'm just moving this around, turning it a bit. So the black dots that you see moving here is the position of the cameras. And then in the middle, you see two dancers that we recorded in December last year, just doing their thing for a project that is ongoing right now. So that is what you do. You record the volume all around, the volume that you're interested in. So we often get the question, why do that? When we can record motion since the time we invented film cameras. But there are some advantages with this in that film cameras can't handle. So an ordinary film camera or video camera today is still only 2D images. So if you are straight in front of the camera and you do a gesture that moves in front of you, it could be hard in a 2D image to see if the gesture is half a meter in front of you or maybe just 20 centimeters in front of you. But with this system, you just turn everything around and you can look at it from the side. So you get the full 3D coverage of it. And then the other important part is that a video camera, I think the original film cameras were 24 frames per second, which is what was needed to make it look like it was motion in the pictures. And today you can get video cameras, cheap video cameras that do 30, maybe even 60 frames per second. But we can, with this system, we normally record at 150 frames per second, and we can record up to 500 frames per second. There was a project last year that used 500 frames per second. So this is a background to what we are going into soon. We have a motion capture system. That is the one we're using, and we are sort of experts in motion capture. So we were contacted a couple of years ago by an organization here in Sweden called Riksteatern. And Riksteatern is a national Swedish theater organization who's funded by the state, and the task is to provide good stage performances, stage entertainment to all of Sweden. So not only the big cities. So Riksteatern has a big place in Stockholm where they produce 30, 40 different productions each year, and then they go on tour, and they really go out on the small village. They perform in schools, in old people's homes, in everywhere. So this is a big organization, and it's divided into a lot of smaller parts, and one of these parts is called Riksteatern Crea, that you see here, and they do theater in sign language, so theater for deaf and hearing impaired people. They contacted us and say, we have this idea. We want to transfer the motions of a sign language speaker onto a digital avatar that is projected on a stage, so that the sign language talking avatar would be understandable, and it can interact with other actors on stage. And we want to do it live streaming. And then we got the question that is title of this presentation: could this be done? And we first said probably not, but come down here and we have a look at it and see what we can do. So we thought a little bit about it, and we did some tests, and then we invited them. This is the first try, where we see to the left, we see Jamila, who's the actor. This is a bit blurry, but it will be clearer when I start playing it. We have the screen in the back where there is a character that we just downloaded from the internet just to receive the motions from the motion capture system. And then to the right, we see Joel, who is the director, and behind him is Mindy, who's the artistic manager. And they're looking, and this is our first try. You can just play it. And there is no sound here, so don't look for that. So we were quite happy with this because we looked into it. Okay, it's the body motions, it's the fingers, and we tried to get everything transferred to the character, the robot-like character you see in the background. So we were quite happy with this and thought we had done a good job. And then we asked Mindy and Joel, what do you think? And they answered, absolutely useless. No point at all. And it was a sort of a lack of understanding between our two groups. Because when I looked into this, I know nothing about sign language before I started this. And I only seen sign language in sort of interpretations on TV and seeing how they move their hands and everything. What I didn't understand was that the face is absolutely crucial to the understanding of sign language. And when they asked us about this question, can you transfer the motions? The face was obvious to them. And to us, who's been working with body language and gestures, we didn't even think about the face. So don't ask me exactly to describe how it works. The description I got from Joel was, well, the words are in your hands and in the gestures, but the grammar of the language are in the face. So he said, when I'm looking at this robot, I see the words, but it makes no sense at all. I can't understand what you're saying, even if I understand the words. So that's the explanation I got. Don't ask me to explain it. So we took this knowledge and developed it further. We needed something to record the face. And also Jamila was complaining about having a lot of markers on her fingers because they were really disturbing when she did the signing. So we looked into a method where we could use some device to record the face and some other device to record the fingers. We found an app for an iPhone that actually captures the face and streams it very well. And we found some special gloves that we used for the fingers. I will show them more later. And here we are in our second try. I need to explain this before I start playing. You still see Jamila, you see the back of her. The motions that she's doing is transferred to a character that is on the screen to the right. You can't see the character because in front of the screen, there is a gaffer-taped laptop. And that laptop is having a Zoom meeting with Ylva that you see on the left screen. They will hopefully understand this when I start playing it. So Jamila is speaking. Her motions is transferred to a virtual character that is on the screen to the left. And what Ylva is seeing is this. So here Ylva is having, she's speaking sign language with an avatar that is streamed live from a real person. And this was, I think, the first time I thought, oh, this might actually work. So what we developed here was a workflow that worked fine for what they wanted to do. And we gave that workflow to Riksteatern, to their people and their technicians, who developed it far better than we could ever have done. And it became a production of The Ghost of Canterville, and it went on tour in Sweden last year, toured for 4 months. And I was lucky enough to get some production photo from Riksteatern. So here is behind the scene in one of the performances. see all the thing, and then Jamila is acting out completely back here. And you see she has the phone in front of her face. She has special gloves that records the fingers. And we also got some footage from a rehearsal. There's no sound in this video either, but this is what it looked on stage when they performed this. And I should say that in most places, Jamila was backstage, really. They set up the whole mocap system backstage. But that is not necessary. They actually did one performance in a town called Sundsvall, where the whole theater group went to Sundsvall, but Jamila stayed in Stockholm, and she played her part from Stockholm, and the others were in Sundsvall, and it's 400 kilometers between those two cities. So you can really stream this. You don't have to be close. You can really stream it as well, so which gives you a lot of interesting possibilities. So this was the project that we've then been working with, and it gave us new tools for ordinary recordings. We were already good at recording the full body motions, but now we had a tool for face tracking, and we had a good tool for finger tracking. And this was, I mean, we have recorded fingers before with a lot of markers on the fingers, but we haven't done face recordings before. So this was new to us. So we started to look into what to do with this. In the original project, they were only interested in streaming the data. They were not interested in recording at all. And for us, it's pretty much the other way around. It's very rarely that we need to stream, but we really need to record the data and make sure that you can save it and work with it later, compare it with other data, work in different ways, whatever you need to do with the data. So the setup here, and I apologize, I realize this is in Swedish, but the setup you can see to the left, we have the motion capture camera system connected to one computer, the one that says QTM, and then we have the gloves connected to another computer, the one that says Hand Engine, and then we have an iPhone with something called the Live Link app. AR-Kit is something that Apple developed. These three computers stream the data to through a local Wi-Fi to another computer. This is the visualization computer using a software called Unreal that I will talk about later on. And then that one was the one that was projected on the screen in the original project. But we wanted to record. So we recorded on the different computers, the mocap computers, the finger computers, and on the iPhone. And it turned out to be quite a painful process to get the data out of them, but an even more painful process to actually synchronize it. And then Carolina came up with this idea, but on the visualization computer, the one after the local Wi-Fi, everything is already synchronized. So why not record in that one? So we started to look into, and there were possibilities to do it, but we needed to find out exactly what is it that is being streamed here. And when it comes to the markers, if you see here to the left, this is what the markers look like. We have 44 markers to represent the full body. And to stream the markers, it's a little bit complicated. And also, when you lose the marker, you get a problem. And if there is some noise in the data, that is also a problem. But the system can do something called a skeleton solver. So to the right here, you see the same recording, but you also see the sort of brownish part in the middle is the calculated skeleton that is based on the markers. And there are two big advantages with using the skeleton. One is if you lose a marker, the skeleton will still be there. The skeleton can still be calculated. And if you occlude markers, the skeleton will still work. And the other one is that the skeleton is its own data structure. So it's easier to stream one skeleton than to stream 44 markers. So we wanted to do that, but we realized we could lose, we will lose some data when we do that. So the method we developed, we still record the markers on the local machine, but now it's much easier to synchronize it. And when it came to the data from the iPhone that recorded the face and from the gloves that recorded the fingers, it's exactly the same data on the recording machine as it is on the visualization machine where we try to do the recordings. So we then looked into the software to use, and it's a game engine called Unreal Engine. And a game engine, that's essentially a software in which you produce computer games. But it's something that is really good to visualize 3D data and also to add interaction with 3D data. And it's very good also at motion capture data. And in this particular version 5.6, there was a package that was added to it called MetaHuman. It existed before 5.6, but then it was sort of a separate package. And in MetaHuman, you can create very lifelike characters and do it very, very easily. It's a very simple procedure to follow. So we decided, let's try that. And I created my own version of me, unfortunately in my underwear with holes in. Sorry about that. We didn't have time to create the clothes for it. And this is where we show you now actually the first recording that we did. And I'm asking Carolina here, what should I do? And she suggests play the drums. So let's have a look at that.
Jag ska spela trumma. Tempos.
Yeah, sorry about that. I never was much of a drummer, but this is the interesting thing here is this is our very, very first try. We didn't even expect it to work, and that's why the character looks a bit wonky, and that's because we haven't calibrated properly, and there were some markers not correctly placed. But we were very happy with this, that you could record this inside Unreal Engine. We have all the motions from the fingers, from the face, and from the body. But we soon ran into some serious problems because this was a short recording. And when we started to do the much longer recordings, well, after 3 minutes, it took forever to save it. And if we tried to do a 5-minute recording, the computer just crashed. No possibility at all. So when we looked into this meta-human character and looked what's beneath the skin, so to speak, it's very, very complicated. There is more than thousands different bones to control the motions. So to record directly onto a meta-human character, it's just not useful at all. So we needed a much simpler rig, and then Carolina started to think about it.
Yes, so for characters in Unreal Engine, you use something called a skeletal mesh asset. And it contains of the character's visual mesh, like the actual 3D model, and the character's skeleton that contains bones. So the bones in the skeleton are controlling how the mesh is moving and deforming. So it doesn't have to be a human, but we will show a human-looking character in this example. So Unreal Engine needs a mesh attached to the skeleton. So you can't import the skeleton directly from the mockup system because it doesn't have a mesh attached to it. You can import an animation or stream the animation data to an existing skeletal mesh in Unreal Engine, but you have to create it in a software outside Unreal first. So we have used Blender for this. So we started by making a recording with our mockup system, and we took the information about the skeleton and bones in that recording, such as the positions of the bones, the names, and the hierarchy in the skeleton. And then we recreated that skeleton in Blender. And we created a mesh that looks just like the bones for the actual bones in the skeleton to control. And this is what you see in the center of this image. And this was to be able to use it as a skeletal mesh asset in Unreal Engine, and also to get the visual feedback of the animation. And then we imported the hand bones and hand meshes used by the gloves, and you see that in the left corner. And we attached that to the same skeleton we just created. So the skeleton down to the hand will be controlled by the mocap system, and the fingers will be controlled by the data stream from the gloves. Then we imported the face mesh used for ARKit in the iPhone and all of its morph targets. So it's the same geometry morphed to show different expression of the face. So the head bone in the skeleton we created before will control the position and rotation of the face mesh. But the animation inside the face will not be using bones, but it will animate the mesh by morphing between the base shape, like the neutral expression there, and the morph targets. And morph targets are also called blend shapes or shape keys, depending on which software you use. So ARKit is tracking how much of an expression or morph target is visible, and it will send that information as a value between 0 and 1 at a frame rate of 60 frames per second. So in the next slide, so this is what one frame can look like. So the phone is tracking Stefan's expression there, and you have like a high value on the eye blink left and right, and a high value on the mouth smile, and then it will update like 60 frames per second. And on the next slide here, you will see all the morph target ARKit tracks one after each other, converted to metahuman. So this is like the value, the highest value on each morph target. Yeah, after so the next slide. So then we exported this skeleton that we created in Blender and all the meshes controlled by it to use as a skeletal mesh asset in Unreal Engine. So no unnecessary bones are in this skeleton. The animation will look like as the data being streamed with the same number of bones, the same size of the bones, and the names. So you don't need to do any retargeting in real time, and I will talk more about retargeting later. It will also record the eye motions, even if we didn't export any eyes in this mesh, but it will be like recorded to use it later.
And an added bonus was that in Unreal, it was really easy to just add a sound recording, a sound track. We just connected a microphone to the Unreal computer, and the data is there. Yeah, this is a bit low, but just to show you that actually the sound can be recorded as well. And this is something that we actually have been struggling with in ordinary computer in the recordings. Because synchronization between the motion capture system and the audio recording system has been a little bit tricky now and then. So this was completely unexpected, but it works really fine as far as we have tried it yet. So we wanted to verify that we could get a good result. So when we did this recording, we also recorded the motion capture from the motion capture system at the motion capture computer, as well as the recording that we did inside Unreal. So in this video clip, you will see the green dots represent the markers, comes from the motion capture system, and the video comes from the motion capture system. And then you have the skeleton and the face and the fingers. That was a simplified rig that Carolina created. And we put them together just to see how good they are synchronizing, to see if the Unreal recording, this is me making mistakes here, so see how good the Unreal recording actually was. And it worked really, really well. We are happy with the result as it is right now. We need to test it for much longer recordings. We have done recordings up to maybe 5 minutes or something like that, and that works fine. But if we go up to 20 or 30 minutes, we need to check if there is any drift in any of the streams. But as it looks, it seems to be really, really good. But we also want to be able to analyze the data, and of course, the data can be exported from Unreal in formats that is well known and used. But I should also point out that inside Unreal, there is possibilities to analyze and look at every single thing that is happening. In this clip, we actually see each of the different motions in the face and the curve. They're moving between 0 and 1. So you can actually get the data from inside Unreal, and inside Unreal do analysis as well. But as I said, you can export it and that works fine. You get everything in one file except the sound, which you need to export separately, but it is synchronized with the other file.
Yes, so animation retargeting. That is when you transfer an animation made for a specific character to another character that might have a different skeleton, maybe a different number of bones, a name of the bones, and proportions. As long as the hierarchy is similar, you can use the retargeting tools in Unreal Engine. And they are getting like better every new version of Unreal. So it's just getting easier and easier. So I don't know if you can play.
Yes. So here we begin with trying to record onto my character, and that didn't work. But here we recorded onto the simplified character and then retargeted it to my character.
Fingers, so we have a couple of gloves that we are using.
And here inside Unreal, it's really easy to manipulate the animations if you want to do that. So everything is in place there. So this is what we came up with, and we looked back at some older projects that we have done. This is a project done by a PhD student back then, Jens Nirme, where he were interested in the temporal aspects of a gesture, the timing of a gesture. So what he did here, he recorded people with our motion capture system, and did also sound recording. And then he took that data and applied it onto a virtual character. It's the character you see here, and with the plan to manipulate this data. This is the first one where nothing is changed.
Precis när han kommer till slutet av de här trappgrejerna så fastnar han med hjulet i räls, tror jag det.
And what he wanted to do was to be able to move the gesture in time. And as you see, there was sort of a key gesture here. And in the second version, he has moved that half a second.
Av de här trappgrejerna så fastnar han med hjulet i räls, tror jag det.
And just to show you can completely remove the gesture as well. So it's a way of manipulating gestures to see how if the understanding changes. Now, when Jens did this, it says 2020, but I think he did most of the work before that. He spent months and months and months on this. When he recorded the fingers, for example, he only recorded the pinky and the index finger, and then he interpolated the motions of the other fingers using those markers, which was really tricky to do. The face motion, you see the mouth moving, and that was only used by a software that analyzed the sound file and formed the mouth according to that. So any eye blink or what the eye is doing is sort of random, put in gestures there. So lots and lots of work that he had to do back then. If we do this with the system that we have developed here and the method we have described today, he could probably have done that in a couple of weeks. And I should say this example you see here is one out of, I think, something like 20 different examples. So the work he did for half a year, maybe even more, could be done in a couple of weeks. We haven't told him. We told his supervisor, and she almost cried. But so that is one thing you can do. So then here we have another example of a project that could have benefited quite a lot from the workflow we have presented. This was something, or it is something, that we're working with the medical faculty, and it's a project where they want to study or sort of screen children for potential ADHD. It's not the diagnostic tool, but sort of screening and finding children that should be looked into more carefully. And it has to do with the motor skills of the child. So the doctor is telling the child to perform certain motions, like walk on your heels or walk on the outside of your foot, or move your arms in a special way. But it's usually sort of an awkward moment when the doctor just telling the child to do certain stuff. So they wanted something more fun for the children. So we developed this app that you run in a VR headset, where the child meets a character that asks the child if she's tried this before. So this is a clip here. So if I start playing it, this is what you see from inside the headset now. And she's speaking Swedish here. So what she's saying is, hello, look at me. We are in virtual reality. Have you tried that before? And now, see if you can do what I can do. And then she shows you the motion. And here is the child then. That's me. But so the children meet this character and have a bit more fun. And at the same time, then the doctors can just watch the child playing around and see the things in the motor functions of the child that could be affecting the way they judge that child. Now, we spent quite a lot of time developing this. We recorded all the motions on there was a student that did all the motions here. So we recorded in the motion capture. We adapted the motions to this character that we developed. We developed the environment around it. We had to record the sound separately and then do some sort of trick with the lip syncing and stuff like that, which took quite a lot of time. I think we spent, 3-4 months developing it. If we had the method we have now that we presented today, with recording the sound, the face, the motions, and recorded in an already prepared environment, we could probably have done it in a week. So hopefully more studies like this could be done, since it's a more easy thing to do. So that was the examples I wanted to give you. So now I just want to sign off with me and the me control character turning off the camera and saying thank you.